In the previous video, we learned how to create PABA in Spartan, and now we just have to think about what can we do with this. Visually, we can't gain too much information from just observing it with our eyes. However, Spartan is special in that it can let you run specialized calculations so that we can find out more information about PABA. For example, one thing that we take for granted is that when we're constructing things like PABA, we press this energy minimization button that fixes up the molecule, makes it look real nice, and also gives us information such as right here where it says energy equals 44.86 kilojoules per mole. So what we want to think about in this video is how do we know how stable a structure is based on its energy level, and let's think about steric hindrance and other things like that. We just really want to think about the chemistry side of making these molecules. To begin with, go up here to the taskbar, and if you glide over your mouse, you can see that this is your calculation section, and we're just going to observe different kinds of calculations that you can run on Spartan. If you press this drop box right here, you can see there's a different variety of like molecular mechanics and quantum mechanics testing that you can do. Right now we want to stick to MMFF, which stands for molecular force field, and if you see that you can hold your mouse over the test and gain more information about what it is and the history behind it. Same goes for the rest of them. So we're just going to say an MMFF, and then we're going to press submit. It will ask you to save, and just go ahead and do so you can get your results back. In the top right corner, it will tell you where in the process it is. Right now we see that for PABA, we have submitted a test, and now we will be waiting for the results. This can take several seconds, or it can take a few minutes. It really just depends on the calculation that you're running and how big and complex your molecule is. So we're just going to wait for that. After you have gotten a message saying that you have completed your test, you can click on output, which is right next to your calculation tab, and you will open up a summary that tells you the name of your molecule, the formula, what test you ran, and so on. Specifically, I want to look at the energy, which says 44.86 kilojoule per mole. Now, if you remember correctly, that should seem very familiar, because when we minimize the energy, we see that the same number, 44.864 kilojoules per mole. So now you can understand that the calculation that Spartan does when you press that button is just running an automatic MMFF test on your molecule. Now that we know how the minimization button works, let's think about what does that result mean. Honestly, by itself, that doesn't really say anything to us. We know that the closer the configuration's energy is to 0, that is the most ideal structure and the most chemically stable. However, when we have nothing to compare it to, we really don't know what 44.86 kilojoules per mole is on a scale of how stable the configuration is to how unstable it is. So let's create a way to compare numbers and see which configuration is better. So when we change the configuration, we don't want to change the chemical formula of the molecule, we just want to change the structure. So one way that you can do this is by rotating bonds. If you go into edit mode and you click directly on a bond that you want to observe, for example this one right here, all you have to do is click on it. Now, we want to study the interaction between these two hydrogens right here. If you press on the bond, you see that this gray bar has popped up on the left side of your screen. If you take your mouse and put it right over that gray bar and left click your mouse and then drag it, you can see that the bond rotates. Now, you can play with it and practice a little bit, but make sure that in the end, this bond is turned so that the hydrogen on the oxygen is pointing away from this hydrogen on the carbon. This is probably a good time to also discuss a technical part about Spartan, is how to maneuver a molecule within your workspace. If you take your mouse and left click on the molecule, you can actually rotate it, which might make it easier to access some of the bonds, but also just to look at the molecule from a different perspective. And then if you right click, you can actually translate that molecule across the work area. but that might be more helpful for what you are doing right now with rotating bonds. So after you have done this, go to calculations and run MMFF for this configuration in which the hydrogen is pointing away versus pointing inwards. Again, this might take a few seconds. Your results will be an output once again, and if you scroll down, we can see that now the energy has changed. We see that instead of 44 etc., it is now 3.3 kilojoules per mole. Now, what does that tell us? What does a lower energy value mean? It means that this is a more chemically stable molecule configuration for PABA, and therefore these two hydrogens have less steric hindrance than they did before. It is important to remember that the absolute energy value from your calculation is only useful as when compared to a result from a different configuration compound using the same calculation methodology. So what I mean by that is, for example, if you go to calculations and with the same configuration of the hydrogen pointing upwards, you run a PM3 test instead of MMFF and run your test, you will get different results. And let's see what those are. If you go to output and you scroll down once more, you see the energy value is negative 289.4672 kilojoule per mole. Now we can still learn from this test, but we just can't compare it to the results that we got from MMFF. So now let's do what we did earlier, but in this case, let's revert that bond back so that the hydrogen is pointing inwards once more. Now if you minimize your energy, you see that this is the result from MMFF, but we want to go to our calculations and run PM3 for this configuration of PABA. Okay, so our results have come in, and let's see what they say. They say that the energy for this is negative 282.87 kilojoules per mole. So remember earlier, we saw that there was a lower number for MMFF when this hydrogen was pointing outwards. And some of you might be thinking, well, you got 289 before, and now you got 282 with the hydrogen pointing in, so maybe this is a better configuration. But you have to keep in mind that the numbers here are negative. So technically, the other configuration with the hydrogen pointing out that resulted in negative 289 kilojoule per mole is still a lower energy value, and therefore a better configuration for PABA. And we verified that through two different tests, MMFF and also PM3.